Now it comes to the topic of formula. A formula actually contains variables and constants. Or sometimes constant may not be there, but at least there should be variables. So in a formula, take this as an example, v equals to 1 over 3 times pi times r squared times h. And we can see that 1 over 3 and pi are constants because they do not change. So these two terms are called constant terms. And for v, r, and h, they are called variables because they can be changed. When we substitute different numbers into r and h, it would give corresponding different numbers of v. And the variable v alone on one side, it is called the subject of the formula. And then we can see how we can use the method of substitution to find a certain value when other variables are given. Let's say if we have r equals to 3 and h equals to 10, then we can substitute these two numbers into this formula, which is the formula of volume of a cone. So if a cone has the radius or base radius equals to 3, the height equals to 10, when we substitute into this formula, the volume of the cone should be 30 pi. And we can see that both 1 over 3 and pi are constant terms, but if we don't want to have too many decimal numbers, we can leave the pi there. And then let's see another example. Let's say we have another formula W equals to mg, which is the formula of weight. And if we substitute m and g with 3 and 10 respectively, the value of W would be equal to 30. Another example is that the Fahrenheit degree, the temperature measurement in Fahrenheit, equals to 9 over 5 C plus 32. So if we have a C of minus 15, the corresponding value of F is, by method of substitution, would be 5. And here is another example. Let's say we have formula C equals to 5 plus 30 over n, which is the cost of printing a poster. So we can see here, the more the number of posters printed, the lower is the cost, the value of cost. So if we find the cost of each poster, and if there are 60 posters to be printed, we can just substitute this number into n, and then we get the number of 5.5. That means if we print 60 posters altogether in one batch, then the cost of each poster will be 5.5. But if we print less, and then the cost will be higher for each poster. Usually it should be like this. So now let's come to another topic, is sequence. Sequence in mathematics is actually a list of numbers arranged in a certain order. There is a pattern in the sequence. And each number in the sequence is called a term. Usually we can use different symbols to represent the terms, such as A1, A2, A3, etc., which can represent the first term, second term, and third term, and so forth. And there are many different types of sequence which are very interesting. They can be categorized into arithmetic sequence, geometric sequence, square numbers, triangle numbers, and Fibonacci sequence. So let's take a look at them one by one. If it is arithmetic sequence, the definition of arithmetic sequence is that the difference between adjacent terms is always the same. Let's say we see 1, 4, 7, 10, 13 as a certain sequence, and we will try to examine what type of sequence is that. We can sense that between each adjacent numbers, there is a difference of 3. So from 1 to 4 is plus 3. From 4 to 7, we need to plus 3 again. And then you can be quite sure about the pattern after you check with 3 to 4 numbers. And you see that there is a constant difference of 3 in between adjacent terms. So you can be quite for sure that it is an arithmetic sequence. And not just addition could be possible. Subtraction between adjacent terms can also be possible, like this sequence 90, 85, 80, 75, 70. You can sense that there is a constant decrease between the terms. So you will check first 90 to 85, that should be a minus 5. And 85 to 80, again a difference of minus 5. And after you check three differences between adjacent terms is again minus 5, you can be quite for sure that this is the pattern. And other examples of arithmetic sequence, we can sometimes work out what could be the following terms. Let's say if we have the sequence we mentioned previously, 1, 4, 7, 10, 13, we already know that between adjacent terms is a plus 3 difference. So if the question asks you to predict what should be the sixth term, which means the next term of the term 13, then you already know it should be plus 3 as the difference. So you just use 13 plus 3 to find the next term. And the seventh term again is the next term of 16. You use 16 to add 3. And then again is 19, the seventh term. And for B, another example we learned previously, there's a constant difference of minus 5 between adjacent terms. So if we need to predict the sixth term, we will simply minus 5 from 70. And then it gives 65. Again, the seventh term, we minus 5 from 65 is 60. It's the seventh term, and so forth. So in this way, we can consecutively find the next term and the next term by adding the same difference or minus the same difference. So apart from arithmetic sequence, there is also another type of sequence called geometric sequence. But this time is not the difference between the adjacent terms is the same. Here's the ratio between adjacent terms is always the same. For example, if we have 4, 8, 16, 32, and 64 as the sequence, we can first check that what type of sequence is that. If we add 4 from 4, it gives 8. But if we further add 4 to 8, it doesn't give 16. So we can know that this is not an arithmetic sequence, because they do not have a constant difference. But we can check with giving them a constant ratio whether it works out. If we multiply 4 by 2, and then it gives 8, and if we further multiply 2, it gives 16, and so forth. So we can be quite sure that it is a geometric sequence. Similarly, here we have another sequence, 81, 9, 3, 1, and 1 over 3. And obviously we can sense by calculation at heart that it is not an arithmetic sequence, because it doesn't have a constant difference between adjacent terms. But we can check with whether it has a constant ratio by multiplying a certain number. So if we multiply 81 by 1 over 3, it gives 9. We further multiply 1 over 3, it gives 3, and so forth. So we can be quite sure that this is a geometric sequence. And similarly, we can always find the following terms according to the pattern of the sequence. Let's say, in the previous example, we have the geometric sequence of 4, 8, 16, 32, and 64, and we already know that the ratio is times 2. So if we need to find the sixth term, we can multiply 64 by 2. It gives the following term. And if we need to find the seventh term, we can simply multiply 128 by 2, and is the seventh term. And similarly here for part 2, part B, we see that the original sequence is 81, 9, 3, 1, and 1 over 3. The ratio is times 1 over 3. So if we need to find the sixth term, we simply can just multiply by 1 over 3, and seventh term so forth. So this kind of sequence is also the same. We can always find the following terms in an easy way. And now it comes to square numbers, which is another type of sequence, and it is very interesting actually. And the definition of square numbers are the products of numbers formed by multiplying themselves. So what does that mean? Actually, we have already known that the area of a square can be found by multiplying the sides. That means, for example, if each side of a square is 2 cm, its area is 2 times 2. If each side of a square is 3 cm, the area is 3 times 3. So the area will be 9m squared, and so forth. So it's similar to finding the area of a square. That's why we call this type of sequence square numbers. So for a square number sequence, the first item should be 1 because it's 1 times 1 equals to 1. And the second item is 2 times 2 is 4. And the third item is 3 times 3 equals to 9, and so forth. So we can predict that the sequence would be 1, 4, 9, 16, 25, and then 36, and then 7 times 7 is 49, and then 8 times 8 is 64. So after 25 should be 36, and then 49, and then 64, and so forth. So when you look at such a sequence, after looking at the first few terms, you already know that, or you already can sense that it's not an arithmetic sequence, because there is no fixed difference between adjacent terms. 1 plus 3 equals to 4, but then 4 plus 5 equals to 9. So it's in no way an arithmetic sequence. But it's also not a geometric sequence as well, because there's no fixed ratio between adjacent terms. It's not like 1 times 4 equals to 4 and then 4 times 4 equals to 16. The ratio is not fixed. So we would, by experience, after the first glance, we already can spot that this should be a square number sequence. So this is quite interesting. And another type of interesting sequence we called triangle numbers. Triangle numbers actually, similar to square numbers, is not there is no fixed ratio or fixed difference between adjacent terms, but still we can still see a pattern there. So triangle numbers are representation of number of dots forming equilateral triangles of consecutive sizes. So what does that mean? Let's say if we try to draw a few equilateral triangles, that means all of the sides are equal. So of course the first little triangle only contains 1 dot. We can assume each side is 1, or it's difficult to give it a number, but for the second item it would be 1 plus 2, because when we arrange the dots, we can see that by arranging the dots in this way, the three sides can be equal. Also, the additional dots, or the additional number of dots, are one more than the previous one. Before is 1, now is 1 plus 2, because 2 is 1 more than 1. So the final number is 3. And interestingly, the next term we add one more row of dots, and this new row, the number of dots is again one more than the previous row. Just similarly to the previous case, 2 dots is one more than the first row. So it's 1 plus 2 plus 3. In accumulation, it adds up to 6. So in this way, you can predict what should be the fourth row if we need to find the third term. After the third row, 3 dots, the fourth row would be one more dots in the fourth row, so it should be 4 dots. So it's 1 plus 2 plus 3 plus 4 in accumulation. It should be 10. So finally, if we look at this example, the fifth item should be 1 plus 2 plus 3 plus 4 plus 5. So it should be 15 dots in the fifth item. So in this case, you can predict that for one additional item, we add one more additional row, and each new row contains one more dot more than the previous row. So this is the case. So another type of interesting sequence is called Fibonacci sequence. Again, there is no fixed ratio or difference between adjacent terms, and is formed by finding every new term by adding the previous two terms together. Let's say the number 2 is found by adding 1 and 1. 1 plus 1 goes to 2. And then the next term after that is found by 1 plus 2 equals to 3. And so forth. The next term 5 is found by 2 plus 3. And the next 8 is found by 3 plus 5. So in this way, you can always predict the next and the next term. Let's say 21st, 21. If you want to find the next one, you add up 13 and 21. It should be 34. And then if you want to find further, you always add up the previous two terms together. You will find the next term. This is called Fibonacci sequence. Now let's take a look at what means general term of a sequence, which is a convenient practice because after figuring out a general term, it enables us to find any specific term inside the sequence without always just finding the next and the next by the previous term. So let's say, first of all, general term, usually we can use a symbol A subscript n to denote that. So for example 1, if we take the square number sequence as an example, the first term we can say A1 equals to 1 square is 1. Second term is 2 times 2, 2 square, 4. The third term is 3 times 3 is 3 square, 9. So the general term of a square number sequence should be A subscript n equals to n to the power 2. Because we can foresee that for the subsequent terms, it's always the number square gives the next term. Another number square gives the next term. So here, for any term we want to find, let's say, if we want to find the fifth term of the sequence, we can simply substitute n by 5, and then we know that the fifth term would be 5 times 5 equals to 25. And if we want to find the 100th term of the sequence, we substitute 100 into the general term, then it gives 100 square or 100 times 100, which is 10,000. So in this way, it's much more convenient that we can find any specific term inside the sequence without finding one by one following the adjacent terms. And now it comes to another example of general term. From this sequence, we can see that the sequence is 6, 12, 18, 24, 30. And then by instinct, we can originally check that adding 6 to 6 gives 12, adding 6 to 12 gives 18. So it is quite obvious that this is an arithmetic sequence, because there is a fixed difference between adjacent terms. And the point is how to find the general term so that it's convenient for us to find any specific term among this sequence. So the first one, we can say the first term A1 equals to 6, so it's 6 times 1. And the second term A2 is 6 times 2 gives 12, and so forth. A3 is 6 times 3, which is 18. So there is a fixed pattern here. We can see that according to which term, there is always 6 times that number. The second term is 6 times 2, and if the number is 3 for the term, is 6 times 3 gives the number. So in general, we can say that for the nth term is always 6 times n. That's why the general term we can conclude that is an equals to 6 times n. In this way, we can always pick any one of the specific term to find out. Like, if we want to find the 10th term is A10, then it's 6 times 10. So the 10th term of this sequence should be 60. And in another case, if we want to find a bigger number, the 99th term, then we simply substitute 99 into the bracket. 6 times 99 is 594. So which means the 99th term of this sequence is 594. That's it. That's why this is more convenient to find a general term first, and then we can always find any specific term.